Demagnetizing field. The demagnetizing field, also called the stray field outside the magnet, is the magnetic field H field generated by the magnetization in a magnet. The total magnetic field in a region containing magnets is the sum of the demagnetizing fields of the magnets in the magnetic field due to any free currents or displacement currents. The term demagnetizing field reflects its tendency to act on the magnetization so as to reduce the total magnetic moment. It gives rise to shape anisotropy in ferromagnets with a single magnetic domain and to magnetic domains in larger ferromagnets. The demagnetizing field of an arbitrarily shaped object requires a numerical solution of Poisson's equation, even for the simple case of uniform magnetization. For the special case of ellipsoids including infinite cylinders, the demagnetization field is linearly related to the magnetization by a geometry-dependent constant called the demagnetizing factor. Since the magnetization of a sample at a given location depends on the total magnetic field at that point, the demagnetization factor must be used in order to accurately determine how a magnetic material responds to a magnetic field. See magnetic hysteresis. Magnetostatic principles. Maxwell's equations. In general, the demagnetizing field is a function of position HR. It is derived from the magnetostatic equations for a body with no electric currents. These are Ampere's law and Gauss's law. The magnetic field and flux density are related by where m 0 \display style mu 0 is the permeability of vacuum and m is the magnetization. The magnetic potential. Uniqueness of the demagnetizing field. Any two potentials that satisfy equations 5, 6, and 7, along with regularity at infinity, are identical. The demagnetizing field HD is the gradient of this potential equation 4. Energy. The energy of the demagnetizing field is completely determined by an integral over the volume V of the magnet. Suppose there are two magnets with magnetizations μ and m2. The energy of the first magnet in the demagnetizing field HD2 of the second is. The reciprocity theorem states that magnetic charge and the pole avoidance principle. Formally, the solution of the equations for the potential is where r is the variable to be integrated over the volume of the body in the first integral and the surface in the second, and is the gradient with respect to this variable. Qualitatively, the negative of the divergence of the magnetization m called a volume pole is analogous to a bulk-bound electric charge in the body, while an m called a surface pole is analogous to a bound surface electric charge. Although the magnetic charges do not exist, it can be useful to think of them in this way. In particular, the arrangement of magnetization that reduces the magnetic energy can often be understood in terms of the pole avoidance principle, which states that the magnetization tries to reduce the poles as much as possible. Effect on magnetization. Single domain. One way to remove the magnetic poles inside a ferromagnet is to make the magnetization uniform. This occurs in single-domain ferromagnets. This still leaves the surface poles, so division into domains reduces the poles further. However, very small ferromagnets are kept uniformly magnetized by the exchange interaction. The concentration of poles depends on the direction of magnetization. See the figure. If the magnetization is along the longest axis, the poles are spread across a smaller surface, so the energy is lower. This is a form of magnetic anisotropy called shape anisotropy. Multiple domains. If the ferromagnet is large enough, its magnetization can divide into domains. It is then possible to have the magnetization parallel to the surface. Within each domain, the magnetization is uniform, so there are no volume poles, but there are surface poles at the interfaces domain walls between domains. However, these poles vanish if the magnetic moments on each side of the domain wall meet the wall at the same angle so that the components in *m are the same. Domains configured this way are called closure domains. Demagnetizing factor. An arbitrarily shaped magnetic object has a total magnetic field that varies with location inside the object and can be quite difficult to calculate. This makes it very difficult to determine the magnetic properties of a material, such as, for instance, how the magnetization of a material varies with the magnetic field. For a uniformly magnetized sphere in a uniform magnetic field H0, the internal magnetic field H is uniform, where M0 is the magnetization of the sphere and G is called the demagnetizing factor, and equals 4/3 for a sphere. This equation can be generalized to include ellipsoids having principal axes in x, y, and z directions such that each component has a relationship of the form. Other important examples are an infinite plate and ellipsoid, with two of its axes going to infinity, which has g equals 4 in a direction normal to the plate, and 0 otherwise, and an infinite cylinder, an ellipsoid with one of. The demagnetizing factors are the principal values of the depolarization tensor, which gives both the internal and external values of the fields induced in ellipsoidal bodies by applied electric or magnetic fields. Notes and references. Further reading.